Okay, so it's welcome back to the session, and it's a great pleasure to have ICTS's very own Ashok Sen. He will tell us about classical gravitational wave tails from the quantum soft theorem.
I'd like to thank the organizers for inviting me to speak at this conference. So my topic today is classical gravitational wave tails, which seems like an out-of-place topic in this conference on quantum mechanics. But hopefully by the end of the talk, we'll see some connection to quantum mechanics. But the talk really is on classical gravitational waves. So let's imagine that there is a violent explosion in space where some stationary system breaks apart into fragments. Now, during this process, there will be emission of gravitational waves. And if we have some detector D that is placed far away, it will detect this wave as ripples of space-time. And one example of such violent explosion are supernova. Now, one can also consider a more general situation where you have a collision in space, where a set of objects come together, interact, and fly apart. And during that process, they can exchange mass, energy, and momentum. And this process will also produce gravitational waves. And one example of such collisions in space is the bullet cluster, which essentially consists of a pair of supercluster of galaxies which are passing through each other at about 1% the speed of light. Now, in general, computing gravitational waves produced during such processes is complicated. And it's complicated due to several reasons. First of all, when the objects are close, they may undergo complicated non-gravitational interactions, as in the case of explosion of supernova, where, for example, the nuclear forces play an important role, and we may not know precisely what kind of forces are taking place. The second complication comes because gravity is described by nonlinear partial differential equations. So even if the interactions were purely gravitational, as in the case of merger of two black holes, the analysis is still complicated. It turns out that surprisingly, some results in quantum theory of gravity, which are known as soft graviton theorems, can be used to get analytical results on some aspects of classical gravitational wave. And this is what I'll try to describe in this talk. And here are my various collaborators on this subject. Alok is a faculty member at Chennai Mathematical Institute. Vishwajit and Arnab are now postdocs in various places. And Devanjan and Babli are students at ICTS. And I should say that in recent years, most of the progress in this field has been due to Vishwajit. In fact, all the papers that I have written recently on this subject have Vishwajit as one of the authors, but he has written many other papers, either by himself or with graduate students from various places. That doesn't include me. So let me begin by giving a brief introduction to this subject. So gravitational radiation is very analogous to electromagnetic radiation. In general theory of relativity, a gravitational field is a symmetric two-index field, which I'll denote by h mu nu, and this measures the distortion of space-time. And this field is sourced by mass or energy. And in my convention that I'll be using, h mu nu will be given by the difference of the metric g mu nu and the Minkowski metric eta mu nu divided by 2, with mu and nu running from 0 to 3. I'll make the notation more clear in the next few slides. So in this notation, gravitational waves will involve time and space varying h mu nu. And the key distinguishing feature that characterizes the wave or a radiation as opposed to a conventional static gravitational field is that at a distance r from the source, the fields fall off as 1 over r and not as 1 over r square or faster. And here when I say fields, I really mean observable part of the fields. in the analog of electromagnetism will be the electric and magnetic fields, okay, will fall off as 1 over r, whereas for, say, electrostatic force field, it falls off as 1 over r square. H mu nu can be measured by a gravitational wave detector like LIGO, and the goal of a theorist is that for a given process, we want to compute H mu nu at a faraway detector. So now let me describe the precise conventions that I'll be using. Okay. So in this talk, at least at the beginning, in the first part of the talk, okay, I'll be keeping all the fundamental constants. I'll not set anything to 1. Okay. So c will denote the speed of light. G will be the Newton's gravitational constant. Space-time coordinates will be denoted by x mu, with mu running from 0 to 3, and x naught being the speed of light times the time coordinate, okay, and x vector at the 3 spatial coordinates. Similarly, momentum will be a 4 vector, with p0 being the energy divided by the speed of light, and p1, p2, p3 are the usual momenta that we are familiar with. Eta mu nu and with eta upper mu nu are the Minkowski metric, 4x4 diagonal matrix, and I'll be using the convention where eta mu nu has mostly plus eigenvalue. So it's a diagonal matrix with the first component being -1, that is associated with the time coordinate or the x naught coordinate, and then the rest are plus. And in this convention, that the inner product between two vectors is given by this, and p square, which is the inner product of p with p, is minus m square c square, according to Einstein's relation between energy and momentum. We'll be using the summation convention, so an index repeated twice is summed over from 0 to 3. And throughout this talk, all the indices will be raised and lowered by the Minkowski metric eta, and not by the full metric g mu nu. Okay. And that's the convention I'll be using. So b mu is given by eta mu rho with times b upper rho, and similarly for a. And finally, I'll be introducing this quantity e mu nu, which is sometimes also called the trace reversed Einstein metric. Okay. This is the definition of eta e mu nu. Okay, rho and sigma are summed over because these are repeated indices. Okay. And I have introduced this symbol because it's often easier to write the various results for e mu nu. Okay. But you don't lose anything by writing the results in terms of e mu nu, because as a consequence of this relation, it also follows that h mu nu can be reconstructed in terms of e mu nu. So if I give the expression for e mu nu, you will be able to construct the expression for h mu nu. So with this, I can now state the results. Okay, so first I'll explain what the results are, and then I'll try to explain where the results come from. Okay. So we go back to our problem, a scattering in space. This is the more general situation, okay, where we take a set of objects of 4 momenta, p1 prime to pm prime. They come together, they interact, and then they disperse as a set of objects with 4 momenta, p1 to pn. Okay. Notice that I have not assumed that the number of particles is conserved. So m particles come in, m objects come in, and n objects go out. We'll choose the origin of space-time to be inside the region S where the scattering event takes place. Okay. This is not a very precise definition, but for whatever formula I'll be writing, we don't need the definitions to be more precise than this. Okay, so there are always errors of order 1 in where the origin of space-time is. Once such a scattering takes place, okay, it sends out gravitational wave signal, and imagine that there is a detector D placed somewhere far away. The signal will reach the detector at some time, okay, and I'll denote by T naught the time at which the peak of the signal reaches the detector. Okay. Again, this is not a very precise definition of T naught, okay, but for our purpose, we will only need the definition of T naught up to errors of order unity. Okay, as you will see, all the formulae that we will have will not be sensitive to a shift in the definition of T naught by terms of order unity. So T naught will be given by the light travel time r over c, But in fact, in gravity, the light travel time also gets additional correction, which is proportional to log of the distance, log of r. And this correction is essentially due to gravitational drag on the gravitational wave. Okay, but this will not need to know what the precise form of the correction is. So we'll be defining retarded time at the detector. Okay, so U basically measures the time at the detector with the origin being at the time where the peak of the signal has reached the detector. And what we'll be focusing on will be on the late and early time tail of the wave, which means that the value of h mu nu at the detector at large positive U and large negative U. And the reason that we will be doing this is not because these are the only important things that we want to study, but these are the only things for which we can say something useful without knowing the details of the scattering process. And as I said, we'll be focusing on the terms that are proportional to R inverse, where R is the distance to the detector. And so here is the first central result that I will be describing. That it turns out that E mu nu at the detector at large negative U, that means at early time, before the peak has reached the detector, has a shape like this. So there is a term proportional to 1 over U times a constant C mu nu. There is a term proportional to 1 over U square log U times another constant G mu nu. And then there are corrections which are lower order. For large positive U, there is a similar set of corrections, but there is also a constant shift. So A mu nu is a constant, B mu nu is constant, and F mu nu are also constants. And the next result that I'll be describing is that these constants that you see here are given solely by the 4 momenta of the ingoing and outgoing objects without requiring any knowledge of the details of the scattering process. So it doesn't care, this formula doesn't care if there is a nuclear explosion that took place during the scattering process. The result is insensitive to what happened during the scattering. It only depends on what momenta went in and what momenta went out. So in the next 2 slides, I'll show you the formula for these constants. This formula will look complicated, but the idea is not to look at the details of the formula, but what is important is that the formula exists in the first place. The fact that you can write down the expressions for these constants in terms of only the momenta of the ingoing and outgoing particles. So here are the formulae for these constants A mu nu, B mu nu, and C mu nu. So let me remind you that A and B controls the form of the waveform in the future, and C controls the form of the waveform in the past. We see that C mu nu depends only on the past ingoing momenta, which is perhaps not a surprise, because you shouldn't know what will happen after the collision if you're looking at the waveform in the far past. But A mu nu and B mu nu, which are the waveforms in the future, depend not only on the future particle trajectories, but also on the past particle trajectories. The past, what came in, so these constants depend on what came in as well as what went out, whereas this depends on only what came in. And similarly, there are more complicated formula for this F and G. These are the coefficients of the 1 over U square log U terms. This is in the future, this is in the past. And again, we see a complicated formula, but the only thing that it depends on are the momenta. And I should have said there is one more thing that it depends on, and that's where the detector is. So R here is the distance to the detector, and N is a 4 vector, which is controlled by the angle at which the detector is placed. So the only dependence is on the momenta and the position and the angle of the detector. So as I said, the details of the formula are not important, but there are some hidden features in this formula that I'll try to point out in the next 2 slides. So you notice here that in the far future, there is a constant piece in the expression for E mu nu, which means that after the gravitational wave has passed through, E mu nu doesn't return to 0, it returns to some constant. okay, which means the metric doesn't return to eta mu nu, but returns to eta mu nu plus a constant. This term had been known for a long time, okay, since the 70s. This is what is called a memory. Okay, that somehow the space-time knows about the passage of the gravitational wave, okay, because it doesn't come back to normal even after the wave has passed. So this represents a permanent change in the state of the detector after the passage of the gravitational wave. These terms are known as the tail terms because they describe the correction to the constant, okay, how the signal approaches the constant, okay, at late time and early time. Okay. So these are called the tail terms, and these are more recent, okay, and these were discovered through the application of the soft theorem that I'll be describing. This part I have already emphasized that these quantities can be expressed in terms of the momenta of incoming and outgoing objects without knowing what forces operated and how the objects move during the scattering. I should also add that these also don't depend on the spins of the particles. Okay. You see that there is nowhere the information about the angular momentum of the ingoing and outgoing objects are involved. That's not because I have assumed that they carry zero angular momentum. They simply don't appear at this order. In contrast, I should say that if you are to compute h mu nu at finite time, it will depend on the details of the scattering process, and it will involve very complicated calculations, okay, because it will depend not only on gravity but also all the other forces that might be acting on these objects. Here is one surprising feature of this formula, okay, which is hidden in this complicated formula that I wrote down. Okay, and the feature is the following. That if we look at the expressions for these constants, these are the ones that control the future. Okay, let me show you again here. Okay, for example, F mu nu, okay, it contains sum over the future particles as well as the sum over the past particles. Okay. Similarly, A and B contains sum over the future particles as well as the sum over the past particles. So in this sum, we have to include the contribution from the outgoing flux of gravitational radiation. Okay. Imagine that during this collision, some gravitational radiation is produced, which also carry away energy and momentum. Okay. We have to include that contribution also in this sum. Okay. And this makes it difficult to apply this formula, because this says that if, in order to make use of this formula, okay, we have to know what kind of finite energy gravitational waves are produced, because their flux also has to be included in the sum over final states. And for A mu nu, indeed, this is unavoidable, and this is what is called a nonlinear memory term, okay, which makes it hard to apply this formula, because you have to actually calculate the full flux of gravitational waves before you can calculate the memory. But it turns out that due to some miraculous cancellation, okay, in the expressions for B mu nu and F mu nu, the contribution from the massless final states can be expressed in terms of the massive state momenta. Okay. And so these massless final states includes any gravitational wave that could be produced in this process, okay, or any other massless particle that could be produced in the process, like photons, okay, or flux of neutrinos. Neutrinos are almost massless, so for this purpose, you can just regard them as massless states. And here is the rule, okay, that in the expression for B mu nu, we can simply drop all the massless particle and radiation contribution in the sum over final states, and then just add this simple term over here, where Pi is the total incoming momentum and Pf is the total outgoing momentum carried by the massive particles. Okay. So you see that we are allowed to drop all the sum over massless particles and write the result purely in terms of the massive particle momenta. Similarly, in F mu nu, we drop massless particles and radiation contribution to the sum over final states and add a contribution like this. And I should add that these are not new formulae. Okay. These are simply a consequence of the formula that I have already shown you. You examine those formulae very somewhat carefully and isolate the contribution of the massless states, and you find that the contribution of the massless states can be rearranged, okay, okay, so that you can express them purely in terms of the massive particle momenta. Okay. And I should just say that this is an observation. Okay. This is not something that can be proven from first principle. It's just that you look at the formulae and you find that the final formula has this peculiar property. Okay. Clearly, this must be having some deeper reason, okay, but at present, it's just an experimental fact. Now, these formulae need to be modified if the incoming or outgoing objects carry charge. Okay. Then there are additional terms in the formula which are known. I have just not shown them. Okay. But the long-range electromagnetic interaction do modify this formula. I started the discussion with the explosion like a supernova or say a merger of two black holes, binary black hole merger. Okay. Those can be regarded as a special case of scattering when the initial state has just one object. Okay. So for example, in this case, C mu nu and G mu nu will vanish. These are the early time shape of the form of the waveform, and E mu nu at late time will take this form. Now, let me emphasize again at this stage that these results that I have quoted, okay, are statements in classical theory of gravity. Okay. They can be derived in principle from purely classical analysis. Nevertheless, they are easier to understand as classical limits of some results in quantum theory of gravity, and these results are known as quantum soft graviton theorem. And as I said, the tail terms that I showed you were first predicted from quantum soft graviton theorem. Okay. But now we do have a fully classical derivation. Okay. Although I should just say that if we didn't know about the existence of this formulae, right, we would have never even tried to find such formulae using classical analysis. So I'll now describe first how soft theorems help us arrive at this formulae. Okay. And then if I have time, I'll also describe the classical analysis. Okay. And from now onwards, I'm going to set C equal to 1. So the outline of the derivation from soft graviton theorem. In quantum theory of fields, the scattering amplitude A gives the probability amplitude for transition from one state to another. And mod A square gives the transition probability from one state to another. Now let's suppose that we know the scattering amplitude A for transition from some incoming state P to some outgoing state Q. Here both P and Q can contain sets of particles. So imagine that P contains a set of ingoing particles, Q contains a set of outgoing particles. Okay. And let's suppose that we know the scattering amplitude for P going to Q. What soft graviton theorem tells us is that it gives the transition amplitude for P going to Q plus some low energy gravitons in terms of the original transition amplitude A that was from P to Q. Okay. Gravitons here are massless particles representing the quanta of gravitational wave, okay, just like the photons are quanta of electromagnetic wave. So let me repeat again. Okay. What soft graviton theorem does is that it tells us that if we know the amplitude for P going to Q, okay, where P and Q may be very complicated states containing multiple particles, okay, then it tells you how to calculate the amplitude for P going to Q plus some low energy gravitons. So this is the result in quantum theory. Okay. And now I'm going to describe how to take the classical limit. So to take the classical limit, we have to first take the states P and Q to consist of very massive objects. Okay, imagine that both P and Q, the external particles that go in and come out, are very massive. Okay. So these could be a pair of stars. Okay, a pair of stars going in and breaks apart into fragments. And everything is described by quantum mechanics. So there is a transition amplitude for this process, a pair of stars going into fragments. Now we compute the transition probability for P going to Q plus m low energy gravitons, each of certain energy which I'll call h bar omega. And momentum h bar omega times n hat, where n is the direction in which the gravitons go. Now, what soft theorem tells us is that this transition probability takes the following form. R is the transition probability for going from P to Q without any soft gravitons, m equal to 0. For m equal to 0, this is the transition amplitude for P going to Q. The dependence on m takes this simple form, a factor s to the power m divided by m factorial. M factorial is the result of both statistics. And perhaps I should remind you that this last year was the 100 years of the seminal paper by S. N. Bose. So it is fitting that Bose statistics plays some role in this analysis. So R will depend on the details of the scattering process. And it's a very complicated object. We don't know how to calculate it, right? Because as I said, R is the transition probability for a pair of stars going into fragments. S is known. S is what the soft graviton theorem tells us. S is known as a soft factor. This depends only on the properties of the incoming and outgoing objects. And it turns out that when you take the classical limit, namely when you take the momenta of the incoming and outgoing objects to be very large, then S becomes very large. The formula for S becomes very large. And now if you look at this answer, this expression over here, you see that this is a transition probability for producing m gravitons. And so quantum mechanics doesn't tell you how many gravitons will be produced. It just gives you the transition probability. But this expression has a sharp maximum at m equal to s for large s. And this means that even though classically you are allowed to produce arbitrary, in quantum mechanically you are allowed to produce arbitrary number of gravitons, in the limit when the external states are very massive, the transition probability peaks around a certain value. And that value is S. So S we can identify as the expected classical number of low energy gravitons. Even though quantum mechanics allows for arbitrary number, classically in this limit, the number, the probability distribution peaks around this classical number. And so once you have determined the number of expected number of low energy gravitons, the energy carried by these is given by S times the energy per graviton h bar omega. From this we can calculate the classical flux of energy carried by gravitational wave of frequency omega. And then this energy flux can be translated back into the time Fourier transform of the gravitational wave form h mu nu expressed as a function of omega. And then the inverse Fourier transform gives the late and early time profile, and this leads to the quoted result. And the reason that we can only talk about late and early time profile is because this formula, the soft formula, is valid for small omega, and small omega translates in the after Fourier transform to large time, which means large positive or large negative times. Now, this is not perfect. There are some shortcomings. This, in fact, works without any glitch for d larger than 5, d5 or larger. So if you are trying to calculate the gravitational waveform in 5 or higher dimensions during a scattering, this is it. You don't have to do anything else. But in d equal to 4, it turns out that the usual soft factor S is infrared divergent. In fact, the S matrix itself is infrared divergent. And so we have to regulate the infrared divergence by physical principles. Second subtlety comes because this analysis proceeds by computation of the energy flux in different frequencies. So it's insensitive to the frequency dependent phase of the waveform because mod square doesn't know about the phase. So this has to be determined by separate computation. Nevertheless, these difficulties can be overcome, and this is what leads to the results that I quoted earlier. In contrast, direct classical analysis is much more complicated, but does not have these shortcomings. So in next few minutes, let me just describe how we go about doing a direct classical analysis to arrive at the same results. So what is the goal? Our goal is to find H mu nu or equivalently E mu nu that is generated during the transition process. So for this, we write down Einstein's equation. And this is where I have written Einstein's equation. Now this doesn't look like Einstein's equation. Einstein's equation is supposed to be nonlinear. But essentially what I have done is that this T mu nu that you see on the right hand side, this includes the usual energy momentum tensor of matter, but also all the nonlinear terms of the Einstein's equation. So this is just a rewriting of the Einstein's equation. This is the standard flat space Laplacian, and everything else is on this side. So this is really a nonlinear partial differential equation involving E mu nu and the particle trajectories. And we may not even know what this partial differential equation is because the interactions may be unknown, right? So the exact form of T mu nu may not even be known. But we will proceed. So we define the time Fourier transform of E mu nu, which will denote by E tilde, which is defined here. And then by examining the form of the properties of the Fourier transform, one can show that if you are looking for a waveform that goes to a constant for large U, this corresponds to the time Fourier transform having a singularity of the form omega inverse for small omega. If you are looking for a waveform that goes as 1 over U for large U, this corresponds to the Fourier transform going as log omega for small omega. And if you are looking for a waveform that goes as log U over U square, this corresponds to the Fourier transform going as omega log omega square. What is common between all of these is that these terms are non-analytic at omega equal to 0. Thank you. Now, non-analytic doesn't mean that it's infinite. Right? These are indeed infinite at omega equal to 0, but this is not. Non-analytic means that if we take sufficiently large number of derivatives with respect to omega and then set omega equal to 0, then these terms would become infinite. And that is indeed true also for this term. Take first derivative and set omega equal to 0, this becomes infinite. Now let's go back to our equation, box C mu nu equal to minus 8 pi g T mu nu. We can formally solve it using the usual flat space Dirac-Green's function. Now of course this is not solution, right? Because T mu nu on this side has very complicated dependence on E mu nu. Nevertheless, we can take this equation and go to large X, and using the properties of the Dirac-Green's function, one can show that if you are interested in going at large X, and if you go to the Fourier transform variable, then E tilde mu nu for large X is given by an expression of this form. Right? This is just algebra involving properties of Dirac-Green's function. So here is this formula again. So in this formula, we can divide this integration region over y into two parts. One I'll call the scattering region, where all the complicated interactions take place. This is of some large size around y equal to 0. The size can be taken as large as you want, so that all the interactions are really inside. And then there is the asymptotic region, which is the complement of S. And the idea is now that the non-analytic terms in E tilde mu nu, non-analytic terms, if you recall, are the ones that give divergent result by taking derivative with respect to omega. Right? Now, if you take derivative with respect to omega, you will bring down more and more powers of y. But however many powers of y you bring down, right, this integral will never diverge from finite regions. So the behavior of E mu nu for large U is insensitive to the contribution from the finite region S in this integral, because those will all give analytic terms in the Fourier transform space. So this means that if we are interested in the non-analytic terms in the expression for E tilde, we can restrict the y integral in the region outside S. In this region, only long-range forces are important. Furthermore, E mu nu is small, and so T mu nu simplifies. And basically what one finds is that the equations can be solved iteratively and give the result quoted earlier. It's still a very complicated procedure, but at least it's simpler than having to solve the full nonlinear partial differential equations. So this is a list of the various equations that go in the iteration. but I'll not go into this. So let me just end with a few comments. So the classical analysis is straightforward, and it does not involve the complications of infrared divergence and phase ambiguity that we had in the quantum soft theorem. But it is good to emphasize that it is a quantum theory that teaches us the right question for which you have simple answers. If you are proceeding with the usual classical setup, then the way you will set up the problem is that you will specify the initial configuration and then evolve it to find a final state and the radiation emitted during the process. That's what you do classically. You set up the initial value problem and then evolve it. This is a very complicated problem with no universal answer. But quantum theory teaches us to specify both the initial and final state of matter and then ask for radiation emitted during the process. And this question has simple answers that we saw. So this is the last slide, possible generalizations. There is reason to believe that the coefficient of u to the minus n minus 1 log u to the n, these terms may also have universal properties, namely they depend only on the moment of the particles. We have good reason to believe that this is so, but we don't know what the expression is, what the coefficients are. Can we compute them? Soft theorem is not useful anymore for n greater than 1. But once we know from soft theorem that the formula exists for n equal to 0 and 1, okay, we can go ahead and rely on classical intuition. This is still some work in progress. Hopefully, we'll learn more about this in the next few months. And then the ultimate goal will be to use these results in reverse. Right? Imagine that we can calculate the coefficient of all of these terms, and they depend only on the initial incoming and outgoing momenta. Okay? Then this gives you infinite amount of data for the moment of the scattering particles. And then the question will be, can we use these results in reverse? By measuring the gravitational waveform in a detector, we can measure the coefficient of these terms, and then can we use this data to reconstruct the initial and final states of the event that led to the production of the gravitational wave. Okay, I'll stop. Thank you.
Anyway, thanks, Ashok, for your characteristically lucid and elegant presentation. We have time for a couple of quick questions. Yeah, we'll take Spenta, then Shankar. Yeah.
Hi, great job.
Thank you.
One comment and one question. One comment is that can we consider these calculations and results as indirect evidence for the existence of gravitons, which we have never observed, even though we talk about quantum gravity all the time? That's one comment. The question is that where are the ringing modes actually hidden in this calculation? The ringing modes, actually, the quasi-normal modes. Yes.
Yeah. So the quasi-normal modes will decay exponentially. Right? So these will turn on after the quasi-normal modes have died.
Oh, I see. Afterwards, actually.
Yeah, because these are power law decay. These are power law decay. Okay. And about your question of whether these imply existence of gravitons. Well, of course, we have used gravitons, right? But I don't claim that these imply existence of gravitons, because you can do a purely classical analysis, right, to arrive at the same results.
Okay. But I think you use gravitons
for
quantum theory, and there is a correct classical result.
Yeah,
it tells you something.
I think it's just about the consistency of gravitons with the classical result, and not.
No, we are not observing. I'm not saying that.
Yeah.
But it's a good hint that they exist, and it's worthwhile doing quantum gravity.
that I agree with.
Shankar.
Ashok, two questions. First question, I was confused by your statement, also alluding to lots of famous people as references about the state of the detector changing.
Yes.
That's called measurement. That happens in every experiment involving a detector. What's so special about gravity wave?
Well,
in every experiment, the state of the detector changes and you look at it, and that's called measurement. I missed something. It sounded like a profound statement, but it's
so this is a classical effect. Right? Normally, you would think that if a wave comes, right, and passes through, then it's a sinusoidal oscillation, and at the end of the wave passing, the field will go back to 0. What is happening here is that the wave is passing, which you can think of as a superposition of sinusoidal waves. But nevertheless, after the wave has passed, right, it doesn't go back to 0.
Okay, we should talk about it separately. I think
Okay.
there is a language problem. My second
no.
question is technical, which is that do you have a cutoff in your soft graviton? Is there a infrared catastrophe here, or there is no infrared catastrophe?
No, there is
in
no
this problem?
infrared catastrophe.
I see.
Because when you do the calculation carefully,
Okay.
you find that the cutoff is actually the frequency omega that we are working at.
I see.
So there is no
Very
real
interesting.
cutoff.
I want to understand that better.
Okay.
I want to talk.
Yeah.
Pragya,
I have a general question, and I don't even know whether the question is correct. Question is, all quantum theories almost in all areas of physics seems to show dimensionality effect, but not classical theories. Do you have any comment on that? Or is the question correct?
No, actually, in this case, even the classical theory depends on dimension, because if you just do a classical analysis, right, you find that in 4 dimensions you have these logarithmic terms, right, in the frequency space, which are essentially a reflection of the infrared divergences that are present in the theory. In 5 dimensions, for example, there will be no logarithmic terms of this kind, right? So even classical theory does depend on dimension in this case.
okay, I think in view of time, and I don't see any questions on Zoom either, let's thank Ashoke again. Again, Ashoke is here for discussions, so I know there were